Good. All right. Thank you. Okay, great. I'm excited to present this to you, and in a similar vein, I'm also I think as Sharon did, there's something that I think I'm trying to learn a lesson from, and let me first acknowledge my students, who many of whom are here, and they're spread out all over the place, but they're really doing the hard work. The issue we're all facing is this huge potential transformation that has enormous impact. As we said yesterday at the debate, that this large data solve vision, solve language, and will it solve robotics? Where's the ChatGPT moment? Now, don't worry, I'm coming back to deformable objects. But so the question is this data. Where are we going to get all this data? And how and when are we going to solve robotics? So this question about data is all you need. I just want to, I'm going to mention this again because I want to come back to it, which is in the end-to-end models, there's a lot of potential, but and many people are noticing scaling effects. But I want to give this example really quickly, which is the Google self-driving vehicle is Waymo is very successful. And if you compare it to Tesla, Tesla has vastly more data, approximately 500 to 1 in scale of data. But Tesla actually does much worse than Waymo in terms of performance. So the implication is that data is not all you need. And I think it's a data plus what I call good old-fashioned engineering. So that is modularity, systems that can be analyzed using basically all of the methods that are in the handbook of robotics. So good old-fashioned engineering is tried and true. It's been around for a long time, has a lot of real strong benefits that I think are important to maintain. The idea of algorithms and metrics. I also want to point out the distinction between the size of the size of the data. So this is an illustration. This is the OXE data set from Google. This is physical intelligence data set that was reported in November. And then these are the sizes, the relative sizes of the data sets for VLMs. So this is just GPT-2. And notice the disks in the lower left corner are size comparisons, okay, roughly to scale. So as you get into the more recent large language models, the robot data sets basically shrink down to approximately a pixel or less. So we can go into details about how I got this number, but roughly it's a factor of 100,000. And so, and this data collection is slow and still challenging, even though we have better tools for doing it. And I think, as Sharon said, her UMI system is great for that. But we're still talking about a vast amount of data to match what's out there for VLMs. So I think what we're going to need is model-free plus model-based methods and how to integrate them together. And this is coming back to how I want to talk about today. So there's a particular architecture that we've developed in the lab, and it's like Sharon did. It's basically by retrospecting on what we were doing in the lab and over the past few years in terms of projects, and then retrofitting them to this framework where we call it MANIP, and it's a modular architecture, and the idea is that we can add modules that are either learned or procedural and into a policy. And the process of doing that is essentially by identifying failure modes when we're performing a task, and then inserting these modules to address them, to correct for them. So here's an example. Sharon mentioned this at the speed folding paper that we did. This is basically very similar to this pling idea. Then we also use friction to help smooth the fabric, but then we also added this cheap trick from from online from the YouTube, which basically is able to do this task very fast for folding shirts. It works. So here's another one is, and that's a two-dimensional problem. Here's a three-dimensional deformable object manipulation problem we call bagging, and that is to take these plastic bags that are ubiquitous and unfold one and put some objects into it. Now, the placement of the objects part is pretty simple if you can get the bag opened up, and that's the challenge. So this is what these bags look like when we're dropping them in, right? And a human has no problem opening these bags up, but very difficult for a robot because the perception is extremely difficult. So what we did was we used this idea of using ultraviolet light, UV light, and special pigments that you can paint onto the bag so that the pigments are invisible under normal light, but they light up in colors under fluorescent, under infrared. So, I'm sorry, UV, ultraviolet light. So what you can do is then the robot can just move around pretty much randomly, and you generate lots and lots of instances of before and after images with the light turned on and off, and you get perfectly labeled images of where those features are, like the bag handles and bag openings. So this is very helpful because then we were able to essentially learn a policy for figuring out how to open up these bags so that we could insert objects. Now, notice the success rates are very low. This is, something we can open up the bag approximately half the time with this method, even after this training. So we went back, and this is where we applied this MANIP architecture. And we noticed that there's one particular failure mode that we always encountered, or was very often encountered, which is where when we could get the bag down, flattened out to some degree, but then we try to lift up one layer of the bag and to open it. And what happens is there's three things that can happen. Either you get no layers, where you're trying to grasp and you just pull up air and then you don't get anything, or you pick up one layer, which is what you want, or the third option is you pick up two layers of the bag, and so now you're no better off because you just sort of just moved it around. So what we did is we just zeroed in on that particular sub-primitive, and here we introduced something that was not learned, well, partially learned, but it was something we called SLIP, which is an interactive perception policy where we're singulating one layer using interactive perception. What we mean by that is we're going to reach down and move in this case, the parallel jaw gripper. We're going to just drag it back across the layer of the bag, and we're going to observe it to identify if we've gotten 0, 1, or 2 layers. And if it's 0 or 2, we keep iterating until we get just one layer. Then we can lift the bag successfully. So here's an example. This is running. It turns out that makes all the difference. And now we're able to do this very successfully, and also it generalizes to other bag materials. So that SLIP primitive. So here is our performance before, and you can see it's pretty poor, ranging from 17 to 40% of success of opening these bags. But the SLIP, which is that blank column there, as you can see now, is dramatically improved. So just by zeroing in and identifying this failure mode, we're able to then insert into this, very naturally into this policy, or into this architecture, another module that other primitives that can address that failure. So the idea is that at every iteration, you're maintaining a system's confidence measure. And by that, it's also doing two things. One, the confidence is really measuring how confident you are in the state, because if you're not confident in your state estimation, then you want to go into another primitive that, this is the interactive perception, a primitive that will allow you to increase your confidence in your state estimation. Or you might be in a state from which you're really unfamiliar or is undesirable. And in that case, you also want to go into another primitive to transfer your state into something that is more compatible with your policies. So either of those two things, that's what figures into that, that variable sigma, are used to select in this meta policy selector, are used to select what policy comes next, what sub-policy or primitive comes next. So you have all these policies, but then the nice thing is you can just insert new policies in here, and you can index them and switch between them. And so some of these, this again, it's a combination of both data-based and good old-fashioned engineering, because the policies can be either one. You don't have to be dogmatic and choose one or the other, but you can mix them and combine them in a natural way. So we also applied this in another problem in deformable manipulation, which is cable untangling. And so we heard about this a little bit earlier today. This is a very useful problem for many different applications. I want to mention, by the way, that we tried ChatGPT for this. And when ChatGPT first came out, we were playing around and we said, okay, let's give it an image of a cable and that we want to untangle. And we asked ChatGPT, how would you untangle that? And it gave us this beautiful answer right away. All right, I'll provide a rough trace of the cable's path using XY coordinates. And then it sort of explained how to go about and untangle it. And I remember we were like, oh my God, it's amazing. It can untangle cables. We're done. And then here's the story. Then we plotted out these XY coordinates that it was telling us it was to do, and it was like this. Okay, so the XY coordinates had nothing to do with the cable, but it was very confident that this is what you needed to do. So this is a nice example, I think, of how hallucination works, and that these systems can be extremely confident and completely wrong. So that doesn't work. What we did do, though, was develop. It's actually been an ongoing project over several years, and I should also acknowledge our partnership with Toyota Research Institute on this, to work with cables. And in this case, it's a combination of methods. We use deep learning and supervised learning to identify knots and also overcrossings and undercrossings, and then combine that with some good old-fashioned engineering to come up with some strategies for removing them. Now, a related problem that we developed, a related sub-problem that we identified, was tracing the cables, just understanding how a cable is, how the path of a cable that's moving, and especially situations like this with many crossings. So you want to be able to trace from one end to the other, and you get to these ambiguous points where the cable, especially if it's a tangential crossing, it can go in multiple ways, and so trying to identify which way the cable is actually going is the challenge. So as you can see in that third image there's a lot of little crossing points and ambiguities. So the key is how do we resolve those? So we do, again, we have this cable tracer that moves along the cable, steps along the cable, but it comes up to these points where there's high uncertainty. So just as I was saying before, this is where there's uncertainty in the policy. So then it's going to do something, and there's a couple things to do. One is to zero in and we added a learned classifier for overcrossings and undercrossings. And it turned out, actually, it was very interesting that you could make use of very subtle shadow effects, because there are shadows. Shadows give you a lot of clues. When you look closely at a cable, you can often tell which is crossing over the other. And then we added some other techniques where we actively move the cable to disambiguate. So if you pull on it a little bit, this is just like what humans would do if you're trying to untangle something. You pull a little and you sort of see what moves, and that tells you what's going on. So again, we were able to insert these primitive blocks into the policy and then rerun it. So we called this, the first version of this, our original version, we called it Handloom, and I forget what the acronym that stands for, but then the new version was called Handloom 2.0. And that's the version with these new primitives inserted into it. And so here's the result, is that with the metric here is percent traced. So again, along the full length of the cable, what percent do you correctly trace? And in Handloom 1.5, in this case, we were getting these kind of levels. So these are different tiers of difficulty. So this is over a number of trials of different cables, something like half, we could trace about half correctly. And once we added these new primitives into using MANIP, the tracing went up significantly. So this is, we're not, certainly not at 100%. And again, over iterations, you can bring it up further, but these are my main point is that it is possible to systematically improve the performance of your policy, overall policy, by systematically targeting where the weaknesses are and then addressing them. So so that's my main point, and I think it's relevant. It comes back to this larger question that we're asking as a community in the debate yesterday. I'll come back to that. In the debate yesterday, and what, you know, how should we be thinking about these things, and should we be dogmatic, right? Is it really one or the other? And I think the answer is, I'm very convinced the answer is both, that we really do need both of these things, and that, and eventually I'll also say, I believe that data will win, but the question is when. And if it's 100,000 years, I don't think we want to wait that long. So there's a much better path, which is to not be dogmatic, be open to inserting good old-fashioned engineering where it's helpful, and use it to bootstrap. So we get these performance to better and better levels, then we collect more data, we use that to keep retraining our models, and then those can eventually become better and better. So that is my position on this, and I'm happy to take any questions. Thank you.
Opening of packs. At least in Europe, in the supermarkets, they come all packed or flat, well positioned.
Okay.
And suddenly it becomes a very hard problem, even though you have a lot of structure there, it's difficult to separation.
Mm-hmm.
So do you think that might be like, have you tried, or this might be the limit of what you can do with parallel liquid?
It's a great question. No, I know what you mean. They come in like a box, and then you just pull one out. And actually, we have this in the US too. Actually, when you go to buy fruit or vegetables, you pull off a ring, and then you have this nightmarish trying to open that thing. Yeah. So it's interesting because humans are pretty good at it. It turns out that if you can do this movement, right, and this is actually something you can't really do with most dexterous hands. Actually, I would bet I'm curious if any of the hands that were on the shop floor, on the exhibition hall, can do this kind of sliding motion, but it turns out that's very important. So no, I think actually you're right. In that case, if it's in a box, you probably can sort of do some sort of translational motions and get that to sort of separate in some way. But then you have that same slip challenge, because once it starts to open, you have to find a way to just pinch that one layer. And that's really where the nuance is. And by the way, I think this is a little bit related to a related point, which is that attention mechanisms are important here. That one thing we often, I think humans very subconsciously pay attention to very subtle nuances of the manipulation task, little features that we don't even think about. But those, if you can find those, you can zero in and be able to resolve those. So I think that might work. So it's a nice challenge to actually try it from the bag. So I'll try and see if I can get some of those. And try. You designed a special gripper. Okay, all right. Well, that helps too. Right. Well, I think that's totally fine. It's whatever works. Yeah. Good.
Great talk. So, quick question: if you are able to maybe code a data driven challenge for this, then you test what test you have.
What challenge? What would be a really hard task?
Yeah, benchmarking. So maybe it's hard, or maybe it's only yours.
Oh, that's a great question. I actually have been thinking about one task that I think will be really hard for robots today, and it's the following: it's just to take a key ring with keys on it, right, and then take the keys off the key ring and rearrange them so they'll all have the teeth facing in the same direction. Okay. Now that's something actually not so easy for even humans to do. Whenever my wife needs to do it, she hands it to me and says, "Can you do this?" Because it's kind of like a very nuanced motion planning problem. It's like the alpha puzzle, but it involves forces. So I think that's a really nice problem. That would be a good grand challenge. I don't know if DARPA would care about it, but that would be a hard problem. Now, is it deformable? I think in a way it is, because it's a key ring is a deformable object, but very, very feisty and difficult to work with. So so I put that out there as a challenge. I will happily pay $100 if anybody can solve that problem in the near future. Okay, not $1 million, but 100. Thanks.
Thank you for the talk. So I think tactile sensing is important for communication, but it seems like it's hard to gather data used with tactile sensing.
Yeah.
Do you think we can get away without collecting the huge amount of data without, or should we also start focusing trying to collect those type of data?
Okay, so that's a great question. I'm actually glad you asked it, because that was the other question I was going to ask Sharon about tactile sensing, because Pat Adelson has a new sensor that's very nice. It could be incorporated into the UMI really naturally. So I think, here's my answer to that, is that in the Da Vinci system for surgeons, that for many years they didn't have tactile. They now do, right? That's a new development, but they didn't. And surgeons were still able to do incredibly nuanced operations. So what I think is going on there is that they're able to compensate and essentially visually learn how to feel. And so I think that is, like in this case with the bags, humans do it with a tactile sense, right? But what we learned, the slip primitive, was essentially to do it visually. So I think you can compensate in certain ways because tactile is so complex. And by the way, gel site, it's wonderful, but you have to understand the human tactile sense has this enormous complex dynamic range. There's a lot going on here in terms of how we actually feel. So it's not clear we have that kind of sensing capability yet. But thank you. Good question.
About your big data plus on because in the CVET about the computing, researchers started to develop tools for the RMDO model. So use APIs from OpenCV, which is kind of an analogy of your good old-fashioned techniques. Do you think that also applies for one?
Which tools for like?
Yeah. So we have APIs for those good old-fashioned engineers. Modules and then VLMs to like coordinates and that's kind of system.
Oh, I see. So saying that if you have a vision system that has uses the VLM but also uses OpenCV primitives as well. Yeah, no, absolutely. So that's exactly what I'm advocating for. Yes, and I think actually VLM off the shelf, OpenCV, all of the tools that are out there are very good and are getting better. And so we can absolutely use them. And in many cases, that's enough, because a lot of the things we're seeing, like in Gemini demonstrations, it's because they're getting better at their training with images and text. So it's very good for that. And then actually, I think what's going on with Gemini is a lot of good old-fashioned engineering under the hood. So yeah. Well, that's the hard part, is that if you want to just cut out all the good old-fashioned engineering and just go directly to actions, right? That's where the scale of the data is going to be very, very large. And that's where I think we have a challenge. So if you want to be a purist and you want to get there, I'd just say, yes, you will, but when? If we might all be, long in our graves by the time we get enough data. So that's what I'm saying. Okay, good, thank you.
Thanks for the talk.
Thanks, Matt.
Quick question on sensors as well.
Yeah.
A lot of the parts are dynamic.
Yeah.
And then sensor obviously is a good choice, but then from the vision side, you feel like higher speed.
Oh yeah, good.
Sensor
Absolutely. I'm glad you brought that up, because actually it also occurred to me too, which is these new event cameras. Very interesting. And I think there's definitely something to be said there. I think I'm very interested in experimenting with them. My intuition is you're absolutely right. Dynamics is very important, and you have high-speed effects and blurring that with the traditional cameras. So being able to do the the event camera. One of my students, Justin Kerr, has a new work on using a foveal camera that has a variable resolution, but it moves, the camera moves at high speed. And I think that those ideas are definitely part of this. Is how do we make use of different camera modalities? Just having I like the mirror idea as well, mirrors on the wrist, but also just that having a sort of cyclopean eye sitting there is not really going to be, I don't think that's the right answer alone. So I think the event camera idea is really, really nice. Right. Yeah, and it could be, yes. I mean, I think that the challenge with the tactile is, there's all kinds of nuance because the tactile is not consistent. And so when you're collecting data, every time you change the surface, you actually have a different sensor. So the data you've collected may not be representative of the new data. So you're mixing all this problem. So I think we still have work to do to get the consistent sensors. That's true for vision as well as tactile. But before we start collecting all the data, because if we collect all the data with the wrong sensor, then we have to start over, right? So good. All right, thank you. All right, good. I should end. I'm going to just show you one last thing, guys. This is a new result, deformable manipulation, and this is not tying. We just we haven't published this yet, but it's a new result on surgical robots. So this was a little bit inspired by the work of what was it, Surgical Transformer, that came out a few months ago. And so I will say they in that paper they used 4 cameras, because they put cameras on the wrists, and to do 1 knot. And here we use only 1 camera, and we're doing double knots. So we get 12 knots with 1 camera. Not that we're competing, all right? But you might say, did you do it with chicken skin? Yes, we can do it with chicken skin too, no problem. So this is an example of good old-fashioned engineering, all right? Doing a task that is being, acclaimed as a big victory for data-driven methods. And I just want to again point this out as you can do that same task very competently, or even better, with good old-fashioned engineering. All right, thank you all.